Welcome everyone, and thank you for joining us for DigitalGlobe's lead webinar series, Learn, Engage, Act, and Discover. My name is Becky Schneider, and I'm the Regional Marketing Programs Manager at DigitalGlobe. And I'm also going to be your host for today's webinar. But before we get started, I'd like to pass along a few tips to everyone to keep in mind while viewing today's webinar presentation. First, all attendees are on mute. So to ask a question, please use the Q&A chat box feature that's located at the right-hand side of your screen. All questions will be answered at the end of today's webinar. Attendees have the option to view today's webinar in full screen. To view in the full screen mode, please click the full screen tab that is located at the top of your screen. And lastly, a link to today's webinar recording will be sent to everyone via email within the next 48 hours. Today's webinar is titled WorldView-3 for Property Evaluation, Operations, and Geology. WorldView-3 is a sensor for natural resource, science, and business applications. Its new capabilities look beyond the image pixels and into minerals, materials, moisture content, infrastructure, and disturbance. Today's webinar will highlight a survey of early case studies and demonstrate a range of methods that you can use immediately. These results can improve decision-making for natural resource, science, and business applications. Today's webinar will be presented by Bill Baugh. Bill joined DigitalGlobe in January of 2013 and serves as a research and development scientist. He received both a Bachelor's of Science degree in Geology and a Bachelor's of Arts degree in Geography from the University of California, Santa Barbara, and a master's degree in geology from the University of Colorado Boulder. Prior to joining DigitalGlobe, Bill supported the National Geospatial Intelligence Agency as an image scientist. So without further ado, I would like to welcome Bill, and let's begin today's webinar.
Hi, I'm Bill Baugh, and today I'm going to speak about WorldView-3 for property evaluation, operations, and geology. In other words, how can you leverage the new capabilities of WorldView-3 to evaluate properties and perform exploration around the world. My background is in geology and hyperspectral remote sensing. When I was in school, I had a dream, maybe not necessarily a unique dream. I think some of us shared it. But what I wanted to do was use spectral remote sensing techniques from a satellite platform at high spatial resolution to find gold. I wanted to look around the world and find pathfinder minerals that would be a cue to bury gold deposits. But back when I was in school, Landsat Thematic Mapper was really the state-of-the-art for a satellite platform, and it simply was not adequate for the job. It had 30-meter pixels and 7 spectral bands. So fast forward to the present, WorldView-3 launched in August of 2014, and it's the real thing. High spatial resolution remote sensing from a satellite platform with spectral content that can tell us about rocks, minerals, and materials around the world. That's what we're going to talk about, WorldView-3 and looking at materials on the ground and evaluating property and geology. So to start out here, this first slide, I'm going to demonstrate the increasing information content with more spectral range. Not only more spectral bands, but spectral range covered. So let's start out over on the left side of the screen. Panchromatic, taken from WorldView-1. It's high resolution black and white. And we can see that there's some mountains in perhaps a desert environment, but that's about the limit of the information content. Moving over to the middle, WorldView-2, true color image. Now, increasing information content. We can see some reds and browns, greens, bleached out areas. There's more information, but it would still take an expert here to interpret this image, and the information content is still limited. The question is, what are the rocks on the ground? Move over to the right here. This is an actual WorldView-3 image made from the SWIR bands, and I'll define SWIR in a few minutes. It's a red, green, blue composite, and notice instantly the bright colors that pop out. Each of these colors corresponds with a different type of rock out there. There's carbonates, such as limestone. There's clays, such as kaolinite. There's alteration minerals, alunite. And these all pop out with a simple red, green, blue composite. So even if that doesn't mean anything to you, notice the increasing information content from black and white to color to shortwave infrared. More spectral range, more information. So we can use these SWIR bands and the definition still coming to perform automated material mapping or automated mineral mapping. These SWIR bands and the definition still coming to perform automated material mapping or automated mineral mapping. So we've put in these SWIR bands and the definition still coming to perform automated material mapping or automated mineral mapping. So we've put in these new spectral bands and had the computer tell us where are the rocks on the ground. And you can see that the clay type minerals correspond with the reds, oranges, and yellows. Micas, sericite, for example, correspond with the shades of green, and carbonates, such as limestone, are the blue shades. So now we've had the computer tell us where these are. That's a big step beyond having an expert geologist interpret an image with limited information content. These are examples of what those rocks look like. And my point here is they look quite similar. They're all shades of brown, green, gray. Kaolinite is a type of clay. That was one of our categories. Limestone is a carbonate. And mica, the actual mica out there is sericite, but this is representative. And the point is they look pretty similar, and yet imagine from space, hundreds of kilometers in orbit, how would you tell those apart? Well, it all comes down to the interaction of these rocks and materials with the light and how that light is reflected back up to the sensor. It gives us a tremendous amount of information about what these materials are, and that's what we're going to cover. This is what WorldView-3 looks like. This is the satellite. It has a primary telescope. It has a secondary instrument called CAVIS. The overall design is based on WorldView-2, a highly successful satellite, so we know it's a proven design, and it has to a certain degree been hot-rodded by adding these SWIR bands, shortwave infrared. The spatial resolution has been improved. Now we have panchromatic at 0.31 meters or 31 centimeters. The multispectral bands, visible in near infrared, at 1.2 meter, and the shortwave infrared collected natively at 3.7 meters, but currently sales are limited to 7.5 meters. That's a licensing restriction. The SWIR is a sweet spot. I keep mentioning SWIR. It stands for shortwave infrared. Why is it the sweet spot? That's my next definition here. Light matter interaction. The sun is our power source. It's our light source, and that sun's energy and light passes through the atmosphere. It hits materials on the ground. I've used a water molecule here as an example, but it could be anything, rocks, steel, fiberglass. The light hits that material, and a couple of things can happen. Really about 5 things can happen, but for simplicity, we're just going to look at 2 of them. It can reflect back up to the satellite to be recorded, or it can be absorbed into the molecule, into the material itself as heat. Transmit is another thing, but I'll leave that for a later discussion. A spectral scientist wants to have both reflection and absorption because it makes natural signatures that tell us about the material. And this is an example of what one of those signatures looks like. So if you just want to think of it as a shape signature, that's certainly one way to look at it. It's also a scientific measurement here. So we have wavelength along the bottom in nanometers, and we have reflectance along this axis. Down here at the bottom, that would be no reflection, very dark. Up at the top, a lot of reflection, very bright. And this is what that signature looks like at different wavelengths. I've labeled with words what we call these different ranges. Ultraviolet is here. That's good for a sunburn. Then we get into the visible. These are the wavelengths that we can see with our eyes, violet, blue, yellow, red, for example. Near infrared is adjacent and beyond the red. We cannot see near infrared, another category of light. And here's shortwave infrared. On my screen it looks like the SWIR got cut off, but it stands for shortwave infrared. It's a range of light beyond near infrared. We cannot see it with our eyes. And this is where a lot of the information content is. To fill out this graphic, we have midwave infrared and longwave infrared. WorldView-3 does not work in those ranges, but I need to cover this part of the spectrum here for the discussion. Notice these deep wells here, these deep shapes. Those are what I call absorption features. Remember I said the molecule is absorbing the energy? That's where it's absorbing it. These are absorption features, and they're a naturally occurring signature that tells us about the material. Now notice that the strong primary absorption features are happening out here in the midwave and the long wave. There's also secondary, smaller absorption features occurring here in the SWIR. These are all signatures that tell us about the mineral. In this case, this is kaolinite, but it's simply an example. Now I want you to notice here that in the visible and near infrared, we don't see any absorption features. There's actually some very weak tertiary absorption features, but they're too weak to show up. And so, see what I'm getting at here? The very strong primary ones are out here where we have a hard time remote sensing. There's some secondary ones that occur here in the SWIR, and really nothing going on out here in the visible and near infrared. So that brings to the last step here, sensing capability. We've been building sensors, satellite platforms, to collect in the visible where we can see in the near infrared for a long time, since the 1970s, perhaps even before. And so it's a very mature engineering capability, but it's very hard to build a sensor that works in the midwave and the long wave. So you can see here that SWIR is a sweet spot. It's the intersection between the naturally occurring signatures that tell us about materials and the engineering capability to collect those signatures. And WorldView-3 has pushed the envelope beyond visible near infrared into the SWIR. And that is what makes this sensor so special. So this is an example of what some of these signatures look like. And I'm going to go into a little more detail here so you can understand the significance. This top one is what we would call a hyperspectral spectrum or a laboratory spectrum. Notice it's very detailed. These absorption features have a lot of texture and content to them, and that can tell you a great deal about the chemistry of the material. Over here there's a peak. This is a green plastic tarp, and this peak of reflection is in the green, and that's why it looks green to us. If we could see in the near infrared, there would also be a very bright range right here. One step down, this would be a WorldView-3 spectrum. Each of these diamonds is a band, and there are 16 bands through this spectral range. Notice how this absorption feature appears here, and another absorption feature, and yet another one. These two here at 1800 and 2400 are unique to plastic, and so that tells us it's a plastic, it's a man-made material. If we look at WorldView-2, which is 8-band visible near-infrared only, we do capture the green peak. We capture a near-infrared peak, which actually could fool somebody into thinking it was vegetation, similar to vegetation, but we miss these diagnostic absorption features of plastic. So the information content is out there in the SWIR. Presenting this a little bit different way, I still have wavelength on the bottom in nanometers. I have the range is labeled across the top, visible, adjacent to that near infrared, and adjacent to near infrared is shortwave infrared or SWIR. This is what people tend to use them for. If you want a visible picture, you need the visible bands. Vegetation has some primary things going on here in the near infrared to tell us about the chlorophyll and the vegetation vigor. Iron has an absorption feature in this range. Man-made materials, so this would include plastic, petroleum, fiberglass, variety of roofing materials. They have features in this range. And then rocks have absorption features out in this range here. So I've labeled each of those categories. And then comparing this to sensors that we may know already, here's Landsat 8. Each of these blue bars is the band sensitivity of a different band. You can see they only have a single band in the man-made and rock range. ASTER was another satellite, a Japanese sensor on a NASA platform that had some SWIR bands on it. The SWIR sensor failed in 2008, but geologists have been able to make effective use of the SWIR with ASTER. However, it had 30-meter pixels in the SWIR, and compare that to the 3.7-meter pixels in the SWIR on WorldView-3. So notice these bands, again, only a single band on ASTER in the man-made range, 5 bands in the rock range, and over here, no band. This band on WorldView-3 is very effective for picking up iron and steel absorption features, but ASTER lacks that. So there's new capabilities compared to ASTER there. So finally, WorldView-2 and 3. These are the 8 visible near-infrared bands that are on both WorldView-2 and 3. On WorldView-3, they're collected at 1.2 meter. These are the 8 SWIR bands on WorldView-3 that are collected at 3.7 meter. Notice we don't have one of the 5 bands here, and I'll address that a little bit later when we're talking about carbonate minerals. Okay, one more way to look at this information. I like to present it a few different ways to help different people absorb it. We again have wavelengths on the bottom. We have the 8 visible near-infrared bands here at 1.2 meter. The 8 SWIR bands at 3.7 meter, and this additional instrument, CAVIS, is for looking at the atmosphere. It's a whole separate instrument. If the pixels were projected to the ground, they'd be 30 meters, and it's looking at water vapor and aerosols primarily in the atmosphere with some additional functionality. But those values will be extracted and used as input to modeling programs to correct for some of the impacts the atmosphere has on the data. So moving forward, I believe I have an example of what those impacts look like. Oh yeah, just a reminder, many commercial satellites, imaging satellites, have only these 4 bands. So I just really want to point out the increased spectral diversity on WorldView-3 compared to many other sensors. So atmospheric compensation, I was talking about the atmosphere having a negative impact on the imagery. This is an area in China near Beijing. Notice that there's some blue-gray haze here caused by scattering of aerosols, but it's variable across the image. There's also some white clouds. The algorithm goes in and maps the aerosols. So this is an aerosol map with red being more aerosol, blue being less. And the algorithm then goes in to correct for that scattering impact. Notice the top image change after. It's the same image, but it's been cleaned up considerably. So this atmospheric compensation has 2 advantages. First, for simple interpretability of the image and making a much nicer looking image. And second, for getting to units that are called reflectance. These are properties of the ground material itself, and they're repeatable, whether it's from day to day at the same location, or whether it's for comparing a library spectrum to an unknown location on the ground to understand the material. Looking a little closer, here's that same area before correction, after correction. Before, after. That's atmospheric compensation, correction to reflectance units, which are necessary for these quantitative spectral techniques and also simply much better for visual interpretation. So let's get to some examples now around the world. What if you're trying to look at an operation that your company owns in a remote part of the world and you want to get a perspective on what's occurring there? For this case, I've taken an oil refinery in Algeria to look at. And just a quick overview, we have some infrastructure here, more here. We have a plateau with cliffs along the edge, and then a lower area that's dominated by red sand dunes. We're going to take a closer look at a variety of targets in this image. So let's start with the refining operation. These are cooling fans. So this is pan-sharpened 30-centimeter color. Notice you can actually see the orientation of the fan blades out there. So perhaps your machinery is throwing an error that the fan's not working correctly. You could have somebody on the ground go take a look at it, but you could also pull an image and take a look and see if the fan blade looks like it's in operating condition. That would give you the option to do that from your home office rather than tasking a busy crew on the ground, for example. And if you're trying to evaluate another facility, perhaps that you're thinking of acquiring, and you don't have access to it yet, you can get in and take a look at the quality of the machinery at this facility. Moving on, this is a flare stack. So when hydrocarbons are being processed, there's excess gases, and it's better to burn them than dump them directly into the atmosphere. So at these flare stacks, there's a pipe that would terminate at a flare stack, and those gases would then be burned as they're emitted. And there's usually a trigger or a small flare or flame that will ignite these gases when they arrive at the flare stack. But what we're looking at here is a pan-sharpened 30-centimeter color image of a burning flare stack. Backing off a little bit, our same flares at the bottom of the image here, but we can see there's 3 pipes which have different terminations, and I don't see any burning activity going on there. Shortwave infrared bands are sensitive to thermal emissions in addition to the materials, so I've made a relative heat map here using the shortwave infrared bands, with the red being the hottest part and the blues and purples being hot but cooler. So we can see now a great deal of intensity from the burning flare, but we can also see a thermal response from these 2 other flare stacks, which tells me that they're online with their trigger flares going and ready to operate, but currently not being used for any flaring operation. So again, we're looking at this facility, and we can see that it's online and ready to operate. So let's look more at hot stuff. I mentioned that these SWIR bands are sensitive to thermal emissions, and that can tell us a great deal. Here's a forest fire in Australia, and this would be a color image on the left. We can see smoke. There's really no information about what's actually happening with the fire. Here's a simultaneous SWIR color composite of that same location, and we can see now a great deal of thermal response from the burning fires. And quite importantly, if you're just using smoke to look at the fire, I don't see anything happening at this fence line, whereas over here we can see there's a lot of hot spots remaining, and those would need to be addressed by a fire crew. Same thing up at the top of the image, many hot spots, but really no information about it in the color image. And then you probably also noticed that the smoke itself becomes transparent in the shortwave infrared band. That's because of the relative size of the particles of the smoke compared to the wavelength of the SWIR. They're simply not scattered in the SWIR wavelengths, but they are scattered and visible. So how about a volcano? This is a volcano in Java, which began erupting in the summer of 2015, or northern hemisphere summer anyway. This is a natural color image of the top of that volcano, and I'm going to point out a few things. There's a huge ash plume coming out of it. There's some white water vapor clouds. There's the forested volcano itself, the ash-strewn summit of the volcano, and then finally there's a caldera with black rock in the top. And this is important. Remember that that rock is black. We'll step ahead to a SWIR color composite. Notice that black rock is actually extremely hot. It's not the glowing lava that we might have seen in a documentary. It's just simply hot rock that's emitting, and the SWIR bands are picking it up as very bright. So it's not bubbling lava, it's hot rock, it's emitting in the SWIR, and we're picking up that temperature emission. Notice that the ash coating the summit is a red-brown color. The ash cloud itself is a rusty red color, and it's differentiating from the water vapor clouds, which remain white. So great deal of information here about this erupting volcano using just the SWIR bands and a quick red, green, blue color composite of 3 of those bands. Property evaluation. Maybe you're looking at a property around the world, thinking of acquiring it, and you want to know something about the materials that the buildings are made of on that property. Some common building materials would be corrugated fiberglass, corrugated steel. They look similar. What can we tell from space? So let's start with an area in Los Angeles. It has a variety of roofing. There's industrial flat rooftops, there's residential, and then there's some other buildings here that are difficult to identify on this image. Also notice there's this unique round building with something dark on the rooftop. Using the SWIR bands and spectral matching techniques, comparing to a library, we can pull out these different roofing categories: solar panel, steel, rubber, fiberglass, EPDM. These are synthetic membrane materials. Ceramic tiles, paint on metal, concrete. So notice many of these industrial buildings are covered with membrane-type materials. Some of them would have concrete, which can be used as a roofing material, and some have steel-based roofing materials. This round building has solar panels coating the top of it, and the residential area showing up primarily, as you'd expect in Los Angeles, red tiles. And that type of analysis can be extended to a very large area, just shown here by backing out. Let's come back to this Algeria facility, and what if you're trying to evaluate it and want to understand some of the construction materials in this facility? There's that flare stack. There's the pipes that are leading to it. There's those cooling towers, cooling equipment. And let's perform the same kind of material analysis, spectral matching, for the categories of painted metal, polymer, which could be some types of paint or polymer, and also the plastic and membrane, and steel. We can see that the pipelines are made of steel, as are the cooling facilities. There's some polymer roofing materials out there, and that these storage tanks are probably coated with a polymer-type paint as well. So spectral advantages, evaluating the materials that are making a facility halfway around the world. Let's come around to mineral mapping. A little bit of theory about why you would want to map minerals, looking for gold buried deep in the ground. There's a variety of methods that can concentrate gold into one location. Gold, if you dig a hole out in your backyard, there's probably not going to be any gold out there, but there's natural processes that can pick up the gold in the rock, move it, and concentrate it in one location, and that becomes your ore deposit. So one of these type of systems would be a hydrothermal. That's where very hot waters are traveling through the regional rock, which is this area down here, and they tend to move and pick up gold when they're very hot under a great deal of pressure and have the right chemistry. Those hot waters can move toward the surface, and when they reach the surface, that would take the form of geysers. For example, Yellowstone is an example of activity occurring right now, probably concentrating gold beneath the geysers. So these hot waters, they really don't like to carry the gold. When something changes, for example, the pressure drops, the temperature drops, maybe the chemistry changes, all that gold falls out of those waters in one location, and that becomes your ore deposit. We still can't see the gold, but what we can see is that these hot waters have altered all the surrounding rock. This altered rock becomes a signature or a target that lets us know that a system existed once in this location that might have been concentrating gold. So what does that look like from satellite? On the left is an actual ASTER image. Remember, that was an older satellite with 30-meter SWIR pixels. And this is an area in Nevada called Cooperite that had one of these hydrothermal systems going on, and all this pink rock out here is the altered rock that was changed by that hydrothermal system. On the right is the same location from WorldView-3, similar bands, and you can see the dramatically increased spatial detail by the higher resolution. So let's zoom in a little bit closer. Actual ASTER pixels on the left, actual WorldView-3 pixels on the right. The colors basically track from one to the other, but the amount of detail is dramatically better. And if you're trying to look at a surface exposure and fit that into an ore deposit model, this has much more information to help you evaluate the geology of this property remotely before you send a team out to the field. You'll save a lot of money by having a better evaluation of the site before you spend the time and money to send your people on the ground. Let's come back to the spectra a little bit and look at what they're telling us about these rocks. This is that same image. We're looking at this area in the bottom left corner that shows up as green. It's a carbonate. This green spectrum is from ASTER, of a carbonate from that location. Notice that we can see a well-formed absorption feature here due to the carbonate. The blue spectrum is the same location from WorldView-3. Remember, we were missing that fifth band? This is the impact here. We don't fully form that absorption feature, but by looking at these three bands here, we've been very effectively able to map carbonates nonetheless. But this is a question that comes up when I'm speaking to geologists, and I just wanted to point out the difference here between ASTER and WorldView-3. Now there's another difference between ASTER and WorldView-3 as well. This is another type of mineral out there, an iron oxide mineral, perhaps jarosite. And we can see the green spectrum is ASTER with no response here due to iron, whereas WorldView-3 is having a very strong iron response in this location, and that's because of this additional band. So WorldView-3 brings a new capability of iron oxide mapping that hasn't been available before, and this will really be an area of new research. Here's a hint for you researchers out there. Get some WorldView-3 data and try to develop some new methods for looking at iron oxide. So coming back to Algeria example, we have a close-up of these cliffs and bluffs, a high flat plateau with cliffs and then sand dunes at the bottom. So typically, as a geologist, when I see a high plateau, I think that there's some kind of strong rock layer protecting something softer beneath. And when the strong rock layer chips away, then it erodes rapidly to form those cliffs. And so let's do a spectral mapping of the rocks here. In this case, we've leveraged some of the ASTER mineral indices for looking at the rock types. The blue shades would be carbonate. So there's, I believe, a hard limestone carbonate layer protecting a softer green clay layer beneath, which leads to these cliffs. The iron oxides are mapped as these sand dunes along the bottom. So different technique, ASTER mineral indices for mapping the rock types out at this location. This is my last example, and I want to say something about efficiency and profitability, which is really what it all comes down to and why you would justify buying satellite imagery for your project. So here we're looking at an open pit mine operation in Australia. I want to take a minute to describe some of the activity that's going on here. In the top right, there's a solid bench. This would be the ore material that contains the gold. Holes are drilled in it and it's blasted to generate, to turn it into rubble here. So in the top center is the rubble that the ore material has been blasted into. There's a very large excavator that's moving the material into these dump trucks. These are giant 200-ton dump trucks that would then haul this material either to the mill where the metal would be extracted or to a waste pile. And somebody on the ground is making a choice. Is this material waste or is it ore? And they're routing it to different locations. This is that same area, but backed off a little bit. You can still see the vehicles. And I know from looking already that this is the ore material here in the center, in the dark gray. And then moving off center is non-ore material. This would be the waste. And yet in this color image, they look almost identical to me. But using a mineral index, we've now mapped the ore material in the red and the waste material in the green. And you can see that the equipment here is working away at the edge of the ore material, as you might expect. Let's take this analysis and look at a different part of the mine. Here's an area, there's a haul road that comes up out of the mine where the ore material would go in the dump trucks to the mill. It's expensive to haul heavy rock around, and the mine operations will tend to dump the waste in unused parts of the mine to save the fuel and the wear and tear on the truck. So all these little divots here, each divot is a 200-ton dump truck load of waste into an unused part of the mine. We applied this same alteration analysis, and the first thing that popped out to me was that at least 7 of these dump piles were showing up as altered material. So the gold is not always present in the altered material, but it is only present in altered material. And so it could potentially mean that they've dumped gold-bearing altered material in their waste pile. There's 7 of these dumps, and I did a little bit of analysis using the ore grade in this mine, 2 grams per ton, 200-ton dump truck load. There's 7 of them, 14 ounces of gold per dump truck load, potentially 100 ounces of gold. and the gold price from earlier this year, $128 an ounce, potentially those 7 piles could represent $120,000 worth of gold dumped in their trash pile. And so this is something that's not visually apparent, but was easy to pull out using the WorldView-3 spectral data. And we have asked the mine operators to go and verify whether these are piles that should be recovered and taken to the mill. So one image could save a great deal of money in streamlining the operations of an open pit mine. This slide is a couple of months old. Each of these little strips is a SWIR image already collected in our archive. So take a look at your area of interest here in the world and see if there's SWIR collected already. My point here is that we're filling the archive as we can. There's already a lot of imagery there. And then new imagery can also be tasked if we haven't covered your area of interest already. To wrap things up here, recall WorldView-3 has 3 primary advantages. It has the shortwave infrared SWIR band, the expanded spectral range. It has a CAVIS instrument to help us improve our atmospheric compensation. It has improved resolution. Recall that reflectance is crucial for quantitative remote sensing and also for high-quality interpretation, visual interpretation of the imagery. SWIR tells us about materials. SWIR penetrates smoke, but not water vapor clouds. SWIR has a thermal response for wildfires, volcanoes, and potentially even very hot operations in a facility. SWIR is a sweet spot between naturally occurring signatures and remote sensing capability. And so with that, I'll close with a nice image of Mount Fuji taken from the side here to show off the agility of the sensor. And thank you very much.
So thank you, Bill, for that very informative presentation. At this time, we're now going to open up the Q&A portion for today's webinar. So if you have a question for Bill, I encourage you to type that into the chat box, and we'll answer them in the order that we received. So thank you again, Bill, for the presentation. As you were presenting, we had some questions that came in from some of our attendees. The first question that came in is a listener would like to know if you could talk a little more about the fire use cases.
Sure, yeah, good question. So the fire use cases fall into a few different categories, and I guess they're all enabled by the smoke transparency. So because of the relationship between the SWIR wavelength and the smoke particle size, the smoke's no longer scattering the light, and it passes through the smoke relatively unchanged in the SWIR band. And so now we can see to the ground, and then because of the thermal response, we can see the hot spots of the fire. So some of those use cases could be, if you're thinking in terms of a facility that your company has around the world, if there's a wildfire occurring around outside the facility and you want to check on what's happening, or if there is a fire occurring at the facility itself and you want real-time information, this would be an excellent way to do so. And then other use cases would be disaster response, for example, directing crews on the ground who are fighting a fire by seeing through the smoke and letting them know where the fire is actively burning and where it has and has not already burned on the ground. And then the volcano as well, looking for areas of hot rock that may not be visibly apparent either.
So your next question that came in is a listener would like to know, how would they apply SWIR to exploration for other types of minerals?
How would they, okay, so how would they apply SWIR to exploration for other types of minerals? So I was speaking about gold deposits here, but the iron oxide absorption that I pointed out at around 900 nanometers is very exciting, and it's a capability that hasn't been available in the past. And so there really is not much in the literature about using these superspectral bands to look at the iron oxides. But the iron oxides really tell you a lot about the chemistry of the alteration. And so to help vector your way into the best part of the ore deposit, It's really valuable to understand the iron oxides, and then also simply looking for iron ore itself, looking at the different iron minerals is valuable. And then as in the example I showed, looking at a facility, what parts of it are made of steel or iron, for example.
So moving on to your next question is a listener would like to know, do you have signatures for differentiating between igneous, sedimentary, metamorphic rocks at a regional level and extract the cracks and crevices?
Yeah, so two-part question. So looking at general rock categories, igneous, metamorphic, and sedimentary. I do have signatures. I primarily use signatures from publicly available libraries, such as from the U.S. Geological Survey, and there's a few others out there. And those do have samples of the different rock categories. And then also for looking at a regional scale, it might be advantageous to train the classifier using the rocks locally. So find some good outcrops in the imagery and select those as examples of your different rock categories, and then use those to train your classifier would be a good approach as well. And you can contact me offline and I can tell you more about some of the publicly available spectral libraries that I like to use.
The next question that came in is, it's kind of a two-part question, and the listener would like to know, how can they get access to the SWIR data and how much does it cost?
Okay. I'm going to back up too because I forgot the second part of the previous question.
Oh, okay.
The other question was linear features.
Okay.
So that's typically done with a filter, a directional filter. There's some good algorithms out there for mapping linear features. And that's probably very well done with the panchromatic. I didn't focus too much on the 30-centimeter panchromatic, but the resolution is so good, it really brings out a lot of the structure in the rock. So that's a good approach. And then the sensitivity of the SWIR to different rock composition can help map out fault locations where you have an abrupt change of rock type across the fault as well. So then I'll move on to the other question. Can you repeat it for me?
How can they get access to SWIR data and how much does it cost?
Okay. For this, I'm going to refer you to a product manager, Casey McCullough. And I think Becky can add his contact information to the screen here. So grab it off of there, and Casey can fill you in on how to get the SWIR data.
Moving on, another question that came in from a listener is, if they wanted to support any mining customers on primary mineral evaluation of a particular site, does DigitalGlobe support with signature libraries along with the imagery?
Part of my job is to help people, enable them, work with the spectral data, and so I just personally enjoy it too. So I'd say contact me with questions about Spectra. But one that I really like is one that's made available by the U.S. Geological Survey online, and I believe it's called SPLIB-06, or if you want to search on that term, I think Becky will type that in, SPLIB-06. And you could also look for the USGS spectroscopy lab in a Google search. And it's quite a big and diverse spectral library.
Another question that came in, this is in regards to CAVIS, and they'd like to know, are we using CAVIS data for correcting atmospheric effects for the slides that you presented earlier?
No, the CAVIS is still with the calibration team, and so I have not worked with any CAVIS data directly myself yet. It is yet to come. The atmospheric compensation work that I was showing uses an existing algorithm that looks within the image itself for information cues, and then does radiative transfer modeling to create the output. So short answer, CAVIS is yet to come.
A listener would like to know, do we know a timing when that's coming, or is it just coming soon?
Just coming soon. I don't have a timing on it. The calibration team is very skilled, but it's a small team, and so they're just taking things one at a time.
That same listener also asked if we have processed reflectance products.
Yes, reflectance data is available. I think that's the question.
Mm-hmm.
Yep.
Moving on, you had a popular presentation, so questions, a lot of questions are coming in, so be patient with us, listeners. Your next question, do you have any experience of soil geochemistry with DigitalGlobe imagery?
I do not have any direct experience with soil geochemistry. I think it's valuable and worth looking at, but I can't really say anything informative on the topic. Some of the spectral libraries that I've mentioned do have examples of different soil types in them. That might be a starting point. And just somewhat of a tangent to it, the SWIR bands are very sensitive to moisture, and so looking at soil moisture, perhaps springs that are caused by fractures in structure allowing water to get to the surface would be effective. But again, I have not personally looked at soil moisture with these bands yet either.
So that listener that had just asked you that question about soil geochemistry, he made a comment that the Gobi Desert environment that they're working on is comprised of dispersed soils and sands from vast amounts of erosion of a major island arc system and mineralizing events that they're certain that are out there. So is that something that they could detect or use by using the DigitalGlobe imagery?
So if I understand the question correctly, the soils out there in the Gobi Desert are derived from different rock sources, such as the island arc. And so I would tend to say that it's likely if the soils were derived from different source rocks that those differences would show up. But I don't have any specific examples. And if there's soils that are more indicative for if you're looking at a placer deposit and the metals or diamonds are contained in a specific source rock soil, that would show up. Okay. And just going on a tangent, I've used the 16 bands as a principal component and looking at color composites of the principal components. And so without knowing specifically what rock type they're telling me, the PCA type analysis was very good at differentiating changes in rock type. So that would point out potentially useful changes and boundaries out in your field area.
Another question that came in is Alyssa would like to know if DigitalGlobe has any case studies where WorldView-3 imagery was done on utility poles and power line evaluation and interpretation. And does active power lines give out any specific signals or temperature differences using SWIR imagery?
I think any electromagnetic emissions from power lines or temperature differences would be too subtle and below the signal to noise. So I'd say no, that we're not going to pick up anything directly. One example that I showed, if you end up getting a copy of these slides and reviewing them, that refinery in Algeria, there's some utility poles in that image, and you can see the sharpness of them. You can see the pole itself. I don't think I was able to pick out any wires between them. And if you're looking at larger utility poles, the type that would be a steel structure, they should have that steel absorption feature to help you pull them out of the imagery to locate them. And I think they're large enough that with the 30 centimeter pan data, you could get quite a bit of detail about those structures.
Another question that came in is, during your presentation, you had talked about ASTER mineral indices, and the listener would like to know if you can talk a little more about that.
Sure. So the ASTER satellite had some similar bands on it, but they're not exactly the same. And Australian scientists in particular developed some mineral indices for ASTER that were very effective at looking at geology. And they have published a number of items on the web. So if you look up, you do a web search on ASTER mineral indices, there's some good papers out there.
In your presentation, you talked about smoke penetration with the SWIR bands. And the listener would like to know, can the smoke penetration see through the clouds?
That's a good question. So the question is, does the smoke transparency in the SWIR extend to water vapor clouds? And the answer is no. that water vapor clouds behave differently than the particles in smoke, and so the water vapor clouds remain opaque. Can't see through those. And actually, notice if you look back at the volcano example, the volcanic ash cloud is also opaque. It's a different particle size in the volcanic ash, and so there's no transparency there.
So we're going to take a couple more questions before we close out today's webinar. One of those questions is a listener would like to know what resolution is available for SWIR data.
So SWIR data is collected natively at 3.7 meter, but we have a limitation, a government limitation on our license that we can only distribute these data at 7.5 meter resolution. So if you buy a SWIR image, the pixel size will be 7.5 meters. Internally, we're able to work with the native resolution data and generate a information layer and distribute the layer only, but not the data that was used to generate it.
On kind of that same note, the listener would like to know, do we have any idea of when possibly 3.7 meter resolution SWIR data might be available?
It's still to be determined, and I know that that some groups are working on making that decision, but it just hasn't come back yet. And I'm eager to hear as well, but don't have a known date for it.
Another question that came in is the listener would like to know, where can they find additional documentation on the band combinations?
The additional documentation on the band combinations, the DigitalGlobe website should have a resources section, and I believe there's then a satellite subsection under that, and it has some white papers on the band combinations. And then I would also recommend looking up those ASTER mineral indices. Some of the papers on that have good information on the band combination. And you're always welcome to email me, too, if you have more specific targets that you're looking at, and I can give you some recommendations.
And our last question for today's webinar is, the listener would like to know, are we currently working with any customers or partners who have successfully used SWIR data?
Yes, definitely. Been working with some major mining companies and some very capable consultants and resellers. And we've been looking at mineral locations and having very good results. The sensor's working as it should, and I would characterize the interactions as the companies being very happy with what they've received so far.
Well, that's going to wrap up the Q&A portion for today's webinar. I'd like to thank Bill again for his very informative presentation, and I'd like to thank everyone for attending today's webinar. If you would like more information or if you have additional questions, I encourage you to reach out to Bill directly. I have listed his email address on the slide. That's going to conclude today's webinar. I thank everyone for attending, and we hope to see you at future events.